Oops, it's time to keep reading Chaos because I'm still bored. That's what I'm gonna do, is read it from the place where I was reading it and take out all these little things along the way. There's a hair. I got pretty far. Oh no, I didn't get that far, never mind. Oh yeah, I remember now. The bookmark. Okay. Oh yeah, pendulum stuff, right? Small nonlinearities were easy to disregard. People who conduct experiments learn quickly that they live in an imperfect world. In the century since Galileo and Newton, the search for regularity in experiment had been fundamental. Any experimentalist looks for quantities that remain the same, or quantities that are zero. But that means disregarding bits of messiness that interfere with a neat picture. If a chemist finds two substances in a constant proportion of 2.0011 one day and 2.003 the next day and 1.998 the day after, he would be a fool to not look for a theory that would explain a perfect 2-to-1 ratio. To get his neat results, Galileo also had to disregard nonlinearities that he knew of: friction and air resistance. Air resistance is a notorious experimental nuisance, a complication that had to be stripped away to reach the essence of the new science of mechanics. Does a feather fall rapidly as a stone? All experience with falling objects says no. The story of Galileo dropping balls off the Tower of Pisa as a piece of myth is a story about changing intuitions by inventing an ideal scientific world where regularities can be separated from the disorder of experience. To separate the effects of gravity on a given mass from the effects of air resistance was a brilliant intellectual achievement. It allowed Galileo to close in on the essence of inertia and momentum. Still, in the real world, pendulums eventually do exactly what Aristotle's quaint paradigm predicted. They stop. In laying the groundwork for the next paradigm shift, physicists began to face up to what many believed was a deficiency in their education about simple systems like the pendulum. By our century, dissipative processes like friction were reorganized, and students learned to include them in equations. Students also learned that nonlinear systems were usually unsolvable, which was true, and that they tended to be exceptions, which was not true. Classical mechanics described the behavior of whole classes of moving objects: pendulums and double pendulums, coiled springs and bent rods, plucked strings and bowed strings. The mathematics applied to fluid and to electrical systems. But almost no one in the classical era suspected the chaos that could lurk in dynamical systems if nonlinearity was given its due. A physicist could not truly understand turbulence or complexity unless he understood pendulums, and understood them in a way that was impossible in the first half of the 20th century. As chaos began to unite the study of different systems, pendulum dynamics broadened to cover high technologies from lasers to superconducting Josephson junctions. I don't know what that is. Some chemical reactions displayed pendulum-like behavior, as did the beating heart. The unexpected possibilities extended. One physicist wrote, to physiological and psychiatric medicine, economic forecasting, and perhaps the evolution of society. Consider a playground swing. The swing accelerates on its way down, decelerates on its way up, and all the while losing a bit of speed to friction. It gets a regular push, say from some clockwork machine. All our intuition tells us that no matter where the swing might start, the motion will eventually settle down to a regular back and forth pattern, with the swing coming to the same height each time. That can happen. Yet, odd as it seems, the motion can also turn erratic. First high, then low, never settling down to a steady state, and never exactly repeating a pattern of swings that came before. The surprising erratic behavior comes from a nonlinear twist in the flow of energy in and out of this simple oscillator. The swing is damped as it is driven. Damped because friction is trying to bring it to a halt. Driven because it is getting a periodic push. Even when a damped driven system is at equilibrium, it is not at equilibrium. And the world is full of such systems, beginning with the weather, damped by friction of moving air and water, and by the dissipation of heat to outer space, and driven by the constant push of the sun's energy. But unpredictability was not the reason physicists and mathematicians began taking pendulums seriously again in the 60s and 70s. Unpredictability was only the attention grabber. Those studying chaotic dynamics discovered that the disorderly behavior of simple systems acted as a creative process. It generated complexity, richly organized patterns, sometimes stable and sometimes unstable, sometimes finite and sometimes infinite, but always with the fascination of living things. That was why scientists played with toys. One toy sold under the name space balls or space trapeze is a pair of balls at opposite ends of a rod, sitting like the crossbar of a T atop a pendulum with a third heavier ball at its foot. The lower ball swings back and forth while the upper rod rotates freely. All three balls have little magnets inside, and once set in motion, the device keeps going because it has a battery-powered electromagnet embedded in the base. The device senses the approach of the lowest ball and gives it a small magnetic kick each time it passes. Sometimes the apparatus settles into a steady rhythmic swinging, but other times its motion seems to remain chaotic, always changing and endlessly surprising. Another common pendulum toy is no more than a so-called spherical pendulum, a pendulum free to swing not just back and forth but in any direction. A few small magnets are placed around its base. The magnets attract the metal bob, and when the pendulum stops, it will have been captured by one of them. The idea is to set the pendulum swinging and guess which magnet will win. Even with just 3 magnets placed in a triangle, the pendulum's motion cannot be predicted. It will swing back and forth between A and B for a while, then switch to B and C, and then just as it seems to be settling on C, jump back to A. Suppose a scientist systematically explores the behavior of this toy by making a map as follows. Pick a starting point, hold the bob there and let it go. Color the point red, blue, or green, depending on which magnet ends up with the bob. What will the map look like? It will have regions of solid red, blue, or will it have... It will. It will have regions of solid red, blue, or green. As one might expect, regions where the bob will swing reliably to a particular magnet, but it can also have regions where the colors are woven together with infinite complexity, adjacent to the red point. No matter how close one chooses to look, no matter how much one magnifies the map, there will be green points and blue points. For all practical purposes, then, the bob's destiny will be impossible to guess. Traditionally, a dynamicist would believe that to write down a system's equation is to understand the system. How better to capture the essential features? For a playground swing or a toy, the equations tie together the pendulum's angle, its velocity, its friction, and the force driving it. But because of the little bits of nonlinearity in these equations, a dynamicist would find himself helpless to answer the easiest practical questions about the future of the system. A computer can address the problem by simulating it, rapidly calculating each cycle. But simulation brings its own problem. The tiny imprecision built into each calculation rapidly takes over, because this is a system with sensitive dependence on initial conditions. Before long, the signal disappears, and all that remains is noise. Or is it? Lorenz had found unpredictability, but he had also found pattern. Others, too, discovered suggestions of structure amid seemingly random behavior. The example of the pendulum was simple enough to disregard, but those who chose not to disregard it found it a provocative message. In some sense, they realized physics understood perfectly the fundamental mechanisms of pendulum motion, but could not extend that understanding to the long term. The microscopic pieces were perfectly clear. The macroscopic behavior remained a mystery. The tradition of looking at systems locally, isolating the mechanisms, and then adding them together was beginning to break down. For pendulums, for fluids, for electronic circuits, for lasers, knowledge of the fundamental equations no longer seemed to be the right kind of knowledge at all. As the 1960s went on, individual scientists made discoveries that paralleled Lorenz's, a French astronomer studying galactic orbits, for example, and a Japanese electrical engineer modeling electronic circuits. But the first deliberate, coordinated attempt to understand how global behavior might differ from local behavior came from mathematicians. Among them was Stephen Smale of the University of California at Berkeley, already famous for unraveling the most esoteric problems of many-dimensional topology. A young physicist making small talk asked what Smale was working on. The answer stunned him. Oscillators. It was absurd. Oscillators, pendulums, springs, or electrical circuits were the sort of problem that a physicist finished off early in his training. They were easy. Why would a great mathematician be studying elementary physics? Not until years later did the young man realize that Smale was looking at nonlinear oscillators, chaotic oscillators, and seeing things that physicists had not learned to see. Smale made a bad conjecture. In the most rigorous mathematical terms, he proposed that practically all dynamical systems tended to settle, most of the time, into behavior that was not too strange. As he learned, things were not so simple. Smale was a mathematician who did not just solve problems, but also built problems for others to solve. He parallayed his understanding of history and his intuition about nature into his ability to announce quietly that a whole untried area of research was now worth a mathematician's time. Like a successful businessman, he evaluated risks and coolly planned his strategy. and he had a Pied Piper quality. I don't know. Where Smale led, many followed. His reputation was not confined to mathematics, though. Early in the Vietnam War, he and Jerry Rubin organized international days of protest and sponsored efforts to stop the trains carrying troops through California. In 1966, while the House Un-American Activities Committee was trying to subpoena him, he was heading for Moscow and attend the International Congress of Mathematicians. There he received the Fields Medal, the highest honor of his profession. The scene in Moscow that summer became an there's too many words that I don't get. Indelible part of the Smale legend. 5,000 agitated and agitating mathematicians had gathered. Political tensions were high. Petitions were circulating. As the conference drew towards its close, Smale responded to a request from a North Vietnamese reporter by giving a press conference on the broad steps of Moscow University. He began by condemning the American intervention in Vietnam, and then, just as his host began to smile, added a condemnation of the Soviet invasion of Hungary and the absence of political freedom in the Soviet Union. When he was done, he was quickly hustled away in a car for questioning by Soviet officials. When he returned to California, the National Science Foundation canceled his grant. Smale's Field Medal honored a famous piece of work in topology, a branch of mathematics that flourished in the 20th century and had a particular heyday in the 50s. Topology studies the properties that remain unchanged when shapes are deformed by twisting or stretching or squeezing. Whether a shape is square or round, large or small, it is irrelevant to topology because stretching can change those properties. Topologists ask whether a shape is connected, whether it has holes, whether it is knotted. They imagine surfaces not just in the 1, 2, and 3-dimensional universe of Euclid, but in spaces of many dimensions, impossible to visualize. Topology is geometry on rubber sheets. It concerns the qualitative rather than the quantitative. It asks, if you don't know the measurements, what can you say about the overall structure? Smale had solved one of the historic outstanding problems of topology, the Poincare conjecture for spaces of 5 dimensions and higher, and in so doing established a secure standing as one of the great men of the field. In the 1960s, though, he left topology for untried territory. He began studying dynamical systems for both subjects. Topology and dynamical systems went back to Henry Poincare, who saw them as two sides of one coin. Poincare, at the turn of the century, had been the last great mathematician to bring a geometric imagination to bear on the laws of motion in the physical world. He was the first to understand the possibility of chaos. His writings hinted at a sort of unpredictability, almost as severe as the sort Lorentz discovered. But after Poincare's death, while topology flourished, dynamical system atrophied. Even the name fell into disuse. The subject to which Smale nominally termed was differential equations. Differential equations describe the way systems change continuously over time. The tradition was to look at such things locally, meaning that engineers or physicists would consider one set of possibilities at a time. Like Poincare, Smale wanted to understand them globally, meaning that he wanted to understand the entire realm of possibilities at once. Any set of equations describing a dynamical system, Lorentz's for example, allows certain parameters to be set at the start. In the case of thermal convection, one parameter concerns the viscosity of the fluid. Large changes in parameters can make large differences in a system. For example, the difference between arriving at a steady state and oscillating periodically. But physicists assume that very small changes would cause only very small differences in the numbers, not quantitative changes in behavior. Linking topology and dynamical systems is the possibility of using a shape to help visualize the whole range of behaviors of a system. Why am I can't, there's so much saliva in my mouth, like, those glands, the salivary glands, what are they doing? I don't know why, it's so weird. Okay, linking topology to dynamical systems is the possibility of using a shape to help visualize the whole range of behavior. Maybe I'm talking too fast. Using a shape to help visualize the whole range of behaviors of a system. For a simple system, the shape might be some kind of curved surface. For a complicated system, a manifold of many dimensions. A single point on such a surface represents the state of a system at an instant frozen in time. As a system progresses through time, the point moves, tracing an orbit across this surface. Bending the shape a little corresponds to changing the system's parameters, making a fluid more viscous or driving a pendulum a little harder. Shapes that look roughly the same give roughly the same kind of behavior. If you can visualize the shape, you can understand the system. When Smale turned to dynamical systems, topology, like most pure mathematics, was carried out with an explicit disdain for real-world applications. Topology's origins Topology's origins had been close to physics, but for mathematicians the physical origins were forgotten and shapes were studied for their own sake. Smale fully believed in that ethos. He was the purest of the pure, yet he had an idea that the abstract, esoteric development of topology might now have something to contribute to physics, just as Poincaré had intended at the turn of the century. One of Smale's first contributions, as it happened, was his faulty conjecture. In physical terms, he was proposing a law of nature, something like this. A system can behave erratically, but the erratic behavior cannot be stable. Stability in the sense of Smale, as mathematicians would sometimes say, was a crucial property. Stable behavior in a system was behavior that would not disappear just because some number was changed. A point. Was just changed a tiny bit. Any system could have both stable and unstable behaviors within it. The equations governing a pencil standing on its point have a good mathematical solution with the center of gravity directly above the point, but you cannot stand a pencil on its point because the solution is unstable. The slightest perturbation draws the system away from that solution. On the other hand, a marble lying at the bottom of a bowl stays there because the marble is perturbed slightly, because if the marble is perturbed slightly, it rolls back. Physicists assume that any behavior they could actually observe regularly would have to be stable, since in real systems tiny disturbances and uncertainties are unavoidable. You never know the parameters exactly. If you want a model that will be both physically realistic and robust in the face of small perturbations, physicists reason that you must surely want a stable model. The bad news arrived in the mail soon after Christmas 1959, when Smale was living temporarily in an apartment in Rio de Janeiro with his wife, 2 infant children, and a mass of diapers. His conjecture had defined a class of differential equations, all structurally stable. Any chaotic system, he claimed, could be approximated as closely as you liked by a system in his class. It was not so. A letter from a colleague informed him that many systems were not so well behaved as he had imagined, and it described a counterexample for a system with chaos and stability together. This system was robust. If you perturbed it slightly, as any natural system is constantly perturbed by noise, the strangeness would not go away. Robust and strange. Smale studied the letter with a disbelief that melted away slowly. Chaos and instability, concepts only beginning to acquire formal definitions, were not the same at all. A chaotic system could be stable if its particular brand of irregularity persisted in the face of small disturbances. Lorenz's system was an example, although years would pass before Smale heard about Lorenz. The chaos Lorenz discovered, with all its unpredictability, was as stable as a marble in a bowl. You could add noise to this system, jiggle it, stir it up, interfere with its motion, and then, when everything settled down, the transients dying away like echoes in a canyon, the system would return to the same peculiar pattern of irregularity as before. It was locally unpredictable, globally stable. Real dynamical systems played a more complicated set of rules than anyone had imagined. The example described in the letter from Smale's colleague was another simple system, discovered more than a generation earlier and all but forgotten. As it happened, it was a pendulum in disguise, an oscillating electronic circuit. It was nonlinear and it was periodically forced, just like a child on a swing. It was just a vacuum tube, really, investigated in the 1920s by a Dutch electrical engineer named Balthasar van der Pol. A modern physics student would explore the behavior of such an oscillator by looking at the line traced on the screen of an oscilloscope. Van der Pol did not have an oscilloscope. Van der Pol did, this is fun. Van der Pol did not have an oscilloscope, so he had to monitor his circuit by listening to changing tones in a telephone handset. He was pleased to discover regularities in the behavior as he changed the current that fed it. The tone would leap from frequency to frequency as if climbing a staircase, leaving one frequency and then locking solidly onto the next. Yet, once in a while, Van der Pol noted something strange. The behavior sounded irregular, in a way that he could not explain. Under the circumstances, he was not worried. Often an irregular noise is heard in the telephone receivers before the frequency jumps to the next lower value, he wrote in a letter to Nature. However, this is a subsidiary phenomenon. He was one of many scientists who got a glimpse into chaos but no language to understand it. For people trying to build vacuum tubes, the frequency locking was important. But for people trying to understand the nature of complexity, the truly interesting behavior would turn out to be the irregular noise created by the conflicting poles of a higher and lower frequency. Frequency. That was wrong though it was. Smale's conjecture put him directly on the track of a new way of conceiving the full complexity of dynamical systems. Several mathematicians had taken another look at the possibilities of the van der Pol oscillator, and Smale now took their work into a new realm. His only oscilloscope screen was his mind, but it was a mind shaped by his years of exploring the topological universe. Smale conceived of the entire range of possibilities in the oscillator, the entire phase space as physicists called it. Any state of the system at a moment frozen in time was represented as a point in phase space. All the information about its position or velocity was contained in the coordinates of that point. As the system changed in some way, the point would move to a new position in phase space. As the system changed continuously, the point would trace a trajectory. For a simple system like a pendulum, the phase space might just be a rectangle. The pendulum's angle at a given instant would determine the east-west position of a point, and the pendulum speed would determine the north-south position. For a pendulum swinging regularly back and forth, the trajectory through phase space would be a loop, around and around, as the system lived through the same sequence of positions over and over again. Smale, instead of looking at any one trajectory, concentrated on the behavior of the entire space as the system changed. As more driving energy was added, for example, his intuition leapt from the physical essence of the system to a new kind of geometrical essence. His tools were topological transformations of shapes in space. Transformations like stretching and squeezing. Sometimes these transformations had a clear physical meaning. Dissipation in a system, the loss of energy to friction, meant that the system's shape in phase space would contract like a balloon losing air, finally shrinking to a point at the moment the system comes to a complete halt. I'll show you the picture at where the word halt. Making portraits in phase space. That's that one. Making portraits in phase space. Traditional time series above and trajectories in phase space below are two ways of displaying the same data and gaining a picture of a system's long-term behavior. The first system, on the left, converges on a steady state, a point in phase space. The second repeats itself periodically, forming a cyclical orbit. The third repeats itself in a more complex waltz rhythm, a cycle with period 3. The fourth is chaotic. That's that thing from the dynamo. That was where that word was on the page. Whoops. The chaos one is just so I don't know. The halt, a complete halt. The balloon losing area, finally shrinking to a point at the moment the system comes to a complete halt. To represent the full complexity of the van der Pol oscillator, he realized that the phase space would have to suffer a complex, new kind of combination of transformations. He quickly turned his idea about visualizing global behavior into a new kind of model. His innovation, an enduring image of chaos in the years that followed, was a structure that became known as the horseshoe. Oh, that's this. Okay, what is it? There we go, okay. To make a simple version of Smale's horseshoe, you take a rectangle and squeeze it top to bottom into a horizontal bar. Take one end of the bar and fold it and stretch it around the other, making a C shape like a horseshoe. Then imagine the horseshoe embedded in a new rectangle and repeat the same transformation, shrinking and folding and stretching. The process mimics the work of a mechanical taffy maker, with rotating arms that stretch the taffy, double it up, stretch it again, and so on until the taffy surfaces become very long, very thin, and intricately self-embedded. Smale put his horseshoe through an assortment of topological paces, and the mathematics aside, the horseshoe provided a neat visual analog of the sensitive dependence on initial conditions that Lorentz would cover in the atmosphere a few years later. There. Whoops. I guess you could fold a piece of paper like that. Maybe. Like taffy, right? Smale's horseshoe. This topological transformation provided a basis for understanding the chaotic properties of dynamical systems. The basics are simple. A space is stretched in one direction, squeezed in another, and then folded. When the process is repeated, it produces a kind of structured mixing familiar to anyone who has rolled many layered pastry dough. A pair of points that ends up close together might have become far apart. Or maybe you couldn't, because you couldn't get the C shape with paper. That's why it's dough, right? I don't know. Or like cookie dough you could do, maybe. Pick two nearby points in the original space and you cannot guess where they will end up. they will be driven arbitrarily far apart by all the folding and stretching. Afterward, 2 points that happen to lie nearby will have begun to arbitrarily fall apart. Originally, Smale had hoped to explain all dynamical systems in terms of stretching and squeezing, with no folding, at least no folding that would drastically undermine a system's stability. But folding turned out to be necessary, and folding allowed sharp changes in dynamical behavior. Smale's horseshoe stood as the first of many new geometrical shapes that gave mathematicians and physicists a new intuition about the possibilities of motion. In some ways, it was too artificial to be useful, still too much a creature of mathematical topology to appeal to physicists, but it served as a starting point. As the 60s went on, Smale assembled around him at Berkeley a group of young mathematicians who shared his excitement about this new work in dynamical systems. Another decade would pass before their work fully engaged the attention of less pure sciences. But when it did, physicists would realize that Smale had turned a whole branch of mathematics back toward the real world. It was a golden age, they said. It's the paradigm shift of paradigm shifts, said Ralph Abraham, a Smale colleague who became a professor of mathematics at the University of California at Santa Cruz. When I started my professional work in mathematics in 1960, which is not so long ago, modern mathematics in its eternity, it's saying it twice. I said the wrong word. In its entirety was rejected by physicists, including the most avant-garde, what does that mean? Mathematical physicists. So, differential dynamics, global analysis, manifolds and mappings, differential geometry, everything was just a year or two behind what Einstein had used, was all rejected. The romance between mathematicians and physicists had ended in divorce in the 1930s. These people were no longer speaking. They simply despised each other. Mathematical physicists refused their graduate students permission to take math courses from mathematicians. Take mathematics from us. We will teach you what you need to know. The mathematicians are on some kind of terrible ego trip, and they will destroy your mind. That was 1960. By 1968, this had completely turned around. Eventually, physicists, astronomers, and biologists all knew they had to have the news. A modest comic mystery. The Great Red Spot of Jupiter. Oh, this is good. My back hurts. How long has it been? I don't know. I think it's been 30 minutes, it's only been 40 to 50 to 60. Who knows? I don't know, but I'm going to read this. A modest cosmic, why am I saying comic? I don't know why. A modest cosmic mystery. The Great Red Spot of Jupiter, a vast swirling oval like a giant storm that never moves and never runs down. Anyone who saw the pictures beamed across space from Voyager 2 in 1978 recognized the familiar look of turbulence on a hugely unfamiliar scale. It was one of the solar system's most venerable landmarks, the red spot roaring like an anguished eye amid a turbulence of boiling eyebrows, as John Updike described it. But what was it? 20 years after Lorenz, Smale, and other scientists set in motion a new way of understanding nature's flows, the otherworldly weather of Jupiter proved to be one of the many problems awaiting the altered sense of nature's possibilities that came with the science of chaos. For 3 centuries it had been a case of the more you know, the less you know. First, astronomers noticed a blemish on the great planet not long after Galileo first pointed his telescopes at Jupiter. Robert Hooke saw it in the 1600s. Donati Creti painted it on the Vatican's picture gallery. As a piece of coloration, the spot called for little explaining, but telescopes got better, and knowledge bred ignorance. The last century produced a steady march of theories, one on the heels of another. For example, the lava flow theory. Scientists in the late 19th century imagined a huge oval lake of molten lava flowing out of a volcano, or perhaps the lava had flowed out of a hole created by a planetoid striking a thin solid crust. The new moon theory. A German scientist suggested, by contrast, that the spot was a new moon on the point of emerging from the... What? Okay. The new moon theory. A German scientist suggested, by contrast, that the spot was a new moon on the point of emerging from the planet's surface. The spot was a new moon on the point of emerging from the planet's surface. I don't know. The egg theory. An awkward new fact. The spot was seen to be drifting slightly against the planet's background, so a notion put forward in 1939 viewed the spot as more or less as a more or less solid body floating in the atmosphere the way an egg floats in water. Variations of this theory, including the notion of a drifting bubble of hydrogen or helium, remain current for decades. The column of gas theory. Another new fact. Even though the spot drifted, somehow it never drifted far. So scientists proposed in the 60s that the spot was the top of a rising column of gas, possibly coming through a crater. Then came Voyager. Most astronomers thought the mystery would give way as soon as they could look closely enough, and indeed the Voyager flyby provided a splendid album of new data. But the data in the end was not enough. The spacecraft pictures in 1978 revealed powerful winds and colorful eddies. In spectacular detail, astronomers saw the spot itself as a hurricane-like system of swirling flow, shoving aside the clouds embedded in zones of east-west wind that made horizontal stripes around the planet. Hurricane was the best description anyone could think of, but for several reasons it was inadequate. Earthly hurricanes are powered by the heat released when moisture condenses to rain. No moist processes drive the red spot. Hurricanes rotate in a cyclonic direction, counterclockwise above the equator and clockwise below, like all earthly storms. The red spot's rotation is anticyclonic. And most important, hurricanes die out within days. Also, as astronomers studied the Voyager pictures, they realized that the planet was virtually all fluid in motion. They had been conditioned to look for a solid planet surrounded by a paper-thin atmosphere like Earth, but if Jupiter had a solid core anywhere, it was far from the surface. The planet suddenly looked like one big fluid dynamics experiment, and there sat the red spot, turning steadily around and around, though undisturbed, or thoroughly unperturbed by the chaos around it. The spot became a Gestalt test. Scientists saw what their intuitions allowed them to see. A fluid dynamicist who thought of turbulence as random noise and noisy had no context for understanding an island of stability in its midst. Voyager had made the mystery doubly maddening by showing small-scale features of the flow, too small to be seen by the powerful earthbound telescopes. The small scales displayed rapid disorganization, eddies appearing and disappearing within a day or less. Yet the spot was immune. What kept it going? What kept it in place? The National Aeronautics and Space Administration keeps its picture in archives, a half dozen or so around the country. One archive is at Cornell University. Nearby, in the early 1980s, Philip Marcus, a young astronomer and applied mathematician, had an office. After Voyager, Marcus was one of a half dozen scientists in the United States and Britain who looked... My eyes are getting really cross-eyed for some reason. My lips are peeling. They're really real good. And I just swallowed the skin of my I'm really insane, right? I don't know what I'm doing. Nobody believes me. I guess, like, I don't understand. That's fine. That's why I'm just gonna take my attention into this page, because then nothing can bother me. I don't know why I'm talking about this right now. It just it happened. Marcus was one of a half dozen scientists in the United States and Britain who looked for ways... Oh, this is page 55, too. Looked for ways to model the red spot. Freed from Ersatz hurricane theory, they found more appropriate analogs elsewhere. The Gulf Stream, for example, winding through the western Atlantic Ocean, twists and branches in subtly reminiscent ways. It develops little waves which turn into kinks, which turn into rings, and spin off from the main current, forming slow, long-lasting anticyclonic vortices. Another parallel came from a peculiar... Why am I sweating so much? A peculiar phenomenon in meteorology known as blocking. Sometimes a system of high pressure sits offshore, slowly turning for weeks or months, in defiance of the usual east-west flow. Blocking disrupted the global forecasting models, but it also gave the forecasters some hope, since it produced orderly features with unusual longevity. Marcus studied those NASA pictures for hours. The gorgeous Hasselblad picture... What is that? Hasselblad pictures of men on the moon and the pictures of Jupiter's turbulence. Since Newton's law is applied everywhere, Marcus programmed a computer with a system of fluid equations. To capture Jovian weather meant writing rules for a massive dense hydrogen and helium resembling an unlit star. The planet spins fast, each day flashing by in 10 Earth hours. The spin produces a strong Coriolis force, the sidelong force that shoves against a person walking across a merry-go-round, and the Coriolis force drives the spot. Where Lorenz used his tiny model on the Earth's weather to print crude lines on rolled paper, Marcus used far greater computer power to assemble striking color images. First, he made contour plots. He could barely see what was going on. And then he made slides, and then he assembled the images into an animated movie. It was a revelation. In brilliant blues, reds, and yellows, a checkerboard pattern of rotating vortices coalesces onto an oval with an uncanny resemblance to the great red spot in NASA's animated film of the real thing. You can see this large-scale spot, happy as a clam, amid the small-scale chaotic flow, and the chaotic flow is soaking up energy like a sponge, he said. You see these little tiny filamentary structures in the background sea of chaos. The spot is a self-organizing system, created and regulated by the same nonlinear twists that create the unpredictable turmoil around it. It is stable chaos. Whoa. As a graduate student, Marcus had learned standard physics. That was my eyes going across. Oh no, I'm at the end of the chapter. Solving linear equations, performing experiments designed to match linear analysis. It was a sheltered existence. But after all, nonlinear equations defy solution, so why waste a graduate student's time? Gratification was programmed into his training. As long as he kept the experiments within certain bounds, the linear approximations would suffice, and he would be rewarded with the expected answer. Once in a while, inevitably, the real world would intrude, and Marcus would see what he realized years later had been the signs of chaos. He would stop and say, "Gee, what about this little fluff here?" And he would be told, "Oh, it's experimental error, don't worry about it." But unlike most physicists, Marcus eventually learned Lorenz's lesson that a deterministic system can produce much more than just periodic behavior. He knew to look for wild disorder, and he knew that islands of structure could appear within the disorder. So he brought to the problem of the Great Red Spot an understanding that a complex system can give rise to turbulence and coherence at the same time. He could work within an emerging discipline that was creating its own tradition of using the computer as an experimental tool. And he was willing to think of himself as a new kind of scientist, not primarily an astronomer, not a fluid dynamicist, not an applied mathematician, but a specialist in chaos. 56, 57, that doesn't have the number 57, life's up and downs. I'm gonna, the bookmark, I have the bookmark, because my eyes are getting really, really crossed. That's because I haven't trained my reading good enough, but I watched Your Healthy Brain, and reading out loud is a good idea, so that's why I did this. So that's why I keep doing this, probably.